Thank you very much for inviting me here, and welcome to all the participants to this presentation. So in the next 15 minutes, I would like to talk about deep learning for Earth observation and also the application of deep learning techniques to glacier mapping. I will also show you more specifically 3 case studies shown from the work taken from the work of some of my students. But let me start with a very brief motivation. Why do we need deep learning in Earth observation? And I guess since you are attending this school, you are very interested in the topic. And probably you are aware of the increasing availability of Earth observation data, geospatial data more in general. We have plenty of images, data acquired by satellites, airborne platforms, UAV, and so on. And this gives us a lot of data and images that we can use to monitor and to map the status of the environment and cities on our planet. Also, I think it's worth mentioning the increasing availability of free and open data, like the data provided by the Copernicus program and the satellite, the Sentinel satellites in particular. But all this availability of data, well, that's great. We can do a lot, but the challenge is how do we make sense out of all this data? So we need to have efficient methods that can extract information that is needed for all the applications that we can develop with this data. So here is where deep learning enters into the scene. I mean, deep learning is nowadays the most effective way to extract information from raw data and produce information in the forms of maps, for instance. And here you see some examples of maps of urban environment, of crops, and as we will talk later about glaciers. Among the many applications that we could mention, I would like to also specifically talk about the opportunity that we have right now to use deep learning and Earth observation data to address some of the most pressing global societal challenges, like those identified by the UN Sustainable Development Goals. So I think here there is great potentials to try to address very challenging societal problems related to food security, related to tenure security. And among the others, of course, I would like to mention here climate action, SDG 13. And in that sense, technology and advances in Earth observation can contribute in developing strategies to mitigate and adapt to climate changes. But let's move shortly to a technical part of this presentation. I will promise you it will not be too long. And I just want to mention, because when we talk about deep learning for image analysis, we cannot avoid talking about convolutional neural networks. And maybe you already have some experience with this kind of neural networks, or I hope you will learn. They are really nowadays the most suitable way, let's say, to analyze in an automated manner images. So just as a comparison with more standard neural networks like multi-layer perceptron, you see a picture here on the upper part of the slide. So typically, most of the machine learning algorithms are designed to take an input a vector of features that describe the objects, and they're designed to solve several inference tasks, for instance, a classification or a regression problem. Convolutional neural networks are specifically designed for spatial data that have a 2-dimensional or 3-dimensional structure. So with several convolutional layers, so the network is able to learn the spatial features that are somehow hidden in the image. So they allow us to identify objects, to to characterize objects, and finally make predictions on, for instance, what type of object is there, what is the class of this object, and so on. Right now, when we talk about image analysis, one of the most common task is semantic segmentation. That means we would like to associate to every pixel in an image a semantic label. Okay, so that is called semantic segmentation according to computer vision literature. And then nowadays, or in the last, let's say 5 years, we have seen a lot of research going on in this field, and several network architectures have been developed for this aim. And here I would like just to mention 3 of them among the many. They are quite popular. The first one is SegNet, then we have UNet. They both follow a so-called encoder-decoder type of structure, where the encoder is learning the features from the image and somehow capturing these images at multiple levels, so in a hierarchical way, starting, let's say, from low-level features related to corners and to edges in the image up to middle and high-level features, component of objects, and so on. The decoder is then somehow spatializing all these features in a way that we can produce pixel-wise prediction. So these are very effective ways to produce pixel-wise maps. So they are very common for mapping exercises. But let's now go towards talking what I think is a very relevant application for your school, and it's about mapping glaciers. We know that glaciers are very sensitive to climate change, so they are, for this reason, very important indicators of changes in climate, in precipitation, and temperatures. So monitoring them is very important for climate models. But glaciers are also a major source of fresh waters, especially in certain parts of the world where water is scarce. So glaciers are fundamental for many activities that requires water, for instance, agriculture. And glacier retreat, which is happening at an increasing pace, is influencing many aspects of our life, is influencing the local hydrology, and more probably even more dangerous at the global level, it's influencing the sea level rise. And of course, it influences the ecosystems, the biodiversity of these areas. So mapping and monitoring how glaciers are evolving in time is very important. I will show you now a few case studies taken from the work of some of my students. So the first one is really in Norway and Svalbard. So this is the work of Prashant Pandit. He just completed his MSc thesis, and he used these 2 areas as case study areas. And he used the GLIMS dataset. It's a global dataset with semi-automated labels of the extent of the glaciers. We use this for training, for validation, and for testing deep learning algorithms. And here you see how the dataset has been split in these 3 different data sets for the 2 case study areas. And then we explored several different neural networks, and we also explored with different combination of features. We wanted to combine both SAR and optical images. So for this reason, we combined in our neural network Sentinel-1 and 2 images. And we also extracted additional polarimetric features to enhance the ability to discriminate the different classes. The output is a binary classification map where we can identify the extent of the glacier. And here you see a table. I will not comment in detail all these results, but we see different metrics, we see different network architectures, and even different loss functions that we use for the training. One of the takeaway message is that combining multiple features is helpful for increasing the accuracy. So combining Sentinel-2 and 1 is an effective way. And also extracting additional polarimetric features helps in enhancing the accuracy. And we reached an F1 score of which is above 90%. Let me move to a second case study. Here now we move to the Alps. Of course, also this is another area in Europe where we have lots of glaciers. And this that I'm presenting is the work of my PhD student, Konstantin. And he actually just started, so he just started working on mapping glaciers. And this is one of the first, let's say, attempt to map glaciers. And he's, again, trying to combine multiple features, including optical, SAR, but also a digital elevation model. And one of the challenges that he's facing, and we are all facing, is that it's relatively simple to map clean glaciers when the ice is clearly visible. But when it's covered by debris, then that makes it quite challenging to detect the glacier under the debris. So we explored a network, one network that fuses the multiple source data. And here you see some of the details of this network structure. Is a unit-like type of network with an encoder and a decoder, as I very briefly mentioned before. And basically it's trained end-to-end to fuse all these data sources and produce a map in the end. Here again, you can see some of the numerical results. And nicely, we also compared against the random forest, a pixel-wise classifier, and which doesn't include any spatial information, and unit, which indeed include all that useful information. So if we just focus on the right column, the intersection over union, we can clearly see that including additional features helps in obtaining more accurate classification, and also that deep learning in particular unit provides better classification accuracies. Here we can see some maps. I think it's useful not just to look at numerical or quantitative results, but really look at the maps. So this is one thing I always suggest to students. Combine a qualitative analysis with a quantitative one. And here it's very important because this allows us to see where are the critical areas. And we can see, for instance, that the critical areas are typically the tongues, the termination of the glaciers, which are often covered by debris. And what we see that is more simple classifier like random forests have problems in these areas. And with our light unit, using all the different data sources, we can actually obtain better results so that the tongue of the glacier is much better classified. I know you want me to stick to the 15 minutes, but I'm afraid maybe I will talk a few minutes more if it's possible. And I want to show you also a third case study, which is in the area of Himalayan area, in an area called Zanskar in the Ladakh region in India. And it's a very important area to study because this is an area where people really depends on the water source coming from the glacier. So it's a relatively arid area where glaciers are fundamental for the living of the people in these areas. They are depending on the water for agriculture and many other economical activities. And therefore, the retreat of glaciers in this area is very problematic and can have severe consequences on population. So this is a study of a student, Sonam, is actually coming from that area, and he recently completed his MSc degree here in ITC. I will just briefly talk about what he did. Basically, he did a multi-temporal analysis. Not only he performed classification, using fully convolutional networks. And here you see a little bit of the data set, but he looked also at the temporal dynamic, how glaciers have been retreating, looking back about 30 years. And again, we used, in this case, we used Lancet data for consistency. And we started from 1994. And I will show you just very quickly some of the results that he obtained. And here you see maps obtained with three different models: a standard unit, an attention unit, and a residual attention unit. Without entering into the details of the models, I think it's good for you, it is interesting to observe how the glacier really has retreated, starting from 1994 to 2009 and up to now. And here you see also maps of 2020. So it's clearly visible how the glaciers has largely retreated. Here, just to be also clear, we are only mapping the area extent, but of course, if we want to understand how significant is retreat, one would have to estimate, for instance, the surface mass balance, which is very important to understand how much indeed the effect of the retreat. Some discussion about this case study area. So he also did some surveys with the people involved and stakeholders. And unfortunately, the agricultural productivity has been decreasing. And one of the reasons is really the water shortage due to the retreat of the glacier. And also some villages have to shift, have to go somewhere else because of this problem. Okay, what are we going to do next? I want to, let's say, conclude this talk by talking about what we are currently planning to do. What I've been showing so far are case studies, and what we see also in the literature a lot, there are studies that are local, they look at the local situation. But what we want to do now is try to capture a global picture, what is happening at the entire global level. And that's what we are trying to do with a project which is called Massive, and is carried out together with the University of Oslo and EURAC Research in Italy. And we are aiming at producing consistent, global and consistent data set of glacier maps with high spatial temporal resolution and dense mass balance time series. Of course, there are many challenges, how to deal with huge amount of data. So for that, we are going to use cloud computing, how to ensure model transferability. How can we make sure that one model trained in one area can be used to map glaciers somewhere else? That's, of course, very, very challenging machine learning problem. So stay tuned. A lot more has to come on this topic. And I hope this has somehow inspired you. It's a very interesting, very challenging problem. And I'm here and happy to answer your questions if you have any. Thank you very much for your attention.